algebraic operations on vectors. Let's talk about the magnitude of a vector. Let's say we have some vector, vector A, and we know what magnitude means. It just means how long is that vector. Well, suppose the component form of this vector is vector a dot 1 comma a dot 2. That means, since I've drawn this as a position vector, that this length here is a1, and this length here, the vertical component, is a sub 2. Well, if I wanted to figure out the length of vector A, I could obviously easily do that using the Pythagorean theorem. And we've done that before. The question is there an easier way? Do I have to draw the picture every time? Do I have to form the right triangle and use the Pythagorean theorem? And the answer is, of course, I don't have to do that if I can develop a formula. The formula is very easy based on the Pythagorean theorem. If I square that component and I square the other leg, I'm going to get the length of vector A squared. Solving for the length of vector A would simply be taking the square root of both sides, and I end up with this marvelous result. If I have a vector A, here's the component form, or here's the ij form, whichever way I have it, then the magnitude of A is always given by square root of the horizontal component squared plus the vertical component squared. Now that I have that formula, finding the magnitude of a vector when it comes in component form or ij form is very, very simple. For example, suppose I have vector p, the vector 4 comma negative 1, and I want to know the magnitude of vector p. I really don't need a picture there. I can just use my formula. It's always the square root of the horizontal component squared plus the vertical component squared. A little bit of simplifying and I've got it. 16 plus 1 is going to be the square root of 17. Obviously, I could get a decimal off the calculator if I wanted one. Okay, how about scalar multiplication, multiplying a vector by a scalar? We've talked about that visually. How would that work algebraically? Well, it works just as simply as you might hope. Let's say vector p is once again the vector 4 comma negative 1, and I want to find a name for the vector 2p. Well, all you have to do to multiply vector p by the scalar number 2 is just multiply each component. In other words, 2 times 4, 8, and 2 times negative 1, negative 2, and that's it. It works just as easy as you might hope. You can see that this has to be the case by drawing a quick picture. Here would be the vector 4, negative 1, starting at 0, 0, and ending at parentheses 4, comma, negative 1. So that's vector p. We already know that vector 2p visually is a vector traveling in the same direction whose length is twice as long. So this red vector would be vector 2p. Well, obviously, since I just put another copy of vector p at the end of the first vector p, this would again travel 4 units over, bringing me to 8, and another 1 unit down, bringing me to negative 2. This must be the point 8 comma negative 2, and therefore vector 2p is the vector 8 comma negative 2. And this works just as easily if you're in ij form. Simply take each component and multiply it by that scalar number. Okay, what about vector addition? Again, we've done that visually. How would that work in component form or in ij form? Once again, this is a very straightforward process. I have vector p, 4 comma negative 1, vector q, 3 comma 3. Let's say I want to form the new vector p plus q. So I want to add together 4, negative 1 and 3 comma 3. Well, all I need to do is add the corresponding components. So add the horizontals, 4 plus 3 is 7. Add the verticals, negative 1 plus 3 is 2. And that's it. Vector p plus q, 7 comma 2. Again, you can convince yourself of this reasonably by drawing some pictures. 4, negative 1 would be this vector. The vector 3, 3 would be this vector. And then to add them, I'll use the parallelogram rule. Fill in the missing pieces there of the parallelogram. And then the resultant vector, the sum vector p plus q, starts where the two vectors started and goes across to that opposite corner. So here is a picture of vector p plus q. And I know my drawing is not perfect, but I think you can reasonably see that this is 7 over and then 2 up, 1, 2. This is the vector 7, comma 2. Okay, same two vectors. What if I wanted to subtract the two vectors? Well, once again, this is very, very simple to do. You're just going to subtract the corresponding components. So if you want to do 4, negative 1 minus the vector 3, comma 3, do 4 minus 3 for the horizontal components, that's 1. And then negative 1 minus 3 would be negative 4. P minus Q is the vector 1, comma negative 4. Once again, I can demonstrate this visually. Let me put on the vector 4, negative 1, and then the vector 3, comma 3. Now, we never did subtraction of vectors visually, but I know that P minus Q is the same thing as P plus negative Q. And I know how to do that visually. Here's vector q right here. Vector negative q would be the same exact vector, same length, but pointed in the opposite direction. So it's going to be right around here. Here's vector negative q. Well, now I can add vector p to vector negative q using that same parallelogram rule. I form the parallelogram, I start where the two vectors start, I go across to the opposite corner. Again, I haven't been drawing my picture super carefully, but it does look pretty reasonable that this is the vector 1, comma negative 4 over 1 and then down 4. The same process can be used if we're working in ij form. Just add or subtract the horizontal components, add or subtract the vertical components. Well, let's try to put it all together then. Here's a fresh example. I've got vector A, 5i plus j, vector B, negative 8i plus 3j. I'm interested in answering some questions about this new vector called A plus B. Specifically, I want to know the magnitude of vector A plus B and its direction angle. Well, probably my best bet here would be to go ahead and write down what vector A plus B is. And again, this is very easy. All I'm being asked to do is add these two vectors together. Well, it's kind of like adding like terms. 5i minus 8i is negative 3i. That's the horizontal components. 1j plus 3j is positive 4j, and that's it. There's my A plus B vector. Okay, let's answer the questions. How am I going to find the magnitude of this new vector I just created? Well, we have a formula for that now. It's the square root of the horizontal component squared plus the vertical component squared. I can quickly work that out. I get 9 plus 16 is 25, and the square root of 25 is 5. So the magnitude of this vector is 5. How about the direction angle? I think here it might be nice to draw a picture. Negative 3i plus 4j means horizontal component negative 3, vertical component is 4. So here's a picture of my vector. We've already determined that this has a length of 5. I can drop the perpendicular if I like. Here's that negative 3. Here's the 4. The direction angle, the theta, is this angle, always the positive angle within one rotation measured from the positive x-axis. How am I going to find that angle? Well, I have a couple of choices. We have mostly been using the tangent function. And so we could write tangent of theta is equal to opposite 4 over adjacent negative 3. Here's the problem though. If I go to the inverse tangent button on my calculator, inverse tangent has never heard of an angle in the second quadrant. Inverse tangent only knows about angles between negative 90 and positive 90. So I can use that on the calculator, but I will have to make some adjustments. Okay, so we have inverse tangent of negative 4/3. That comes out to be about negative 53.1 degrees. Well, that's obviously not angle theta. What is it? It is the corresponding symmetric fourth quadrant angle. The inverse tangent button knows about angles here, where this would be a 4, and this would be the 3. Obviously, the 4 would be negative here, and this would be the 5. It's all very symmetrical. Here's the negative 53.1 degrees. How do I move from there to the angle I want? Well, it's obviously just exactly 180 degrees past that spot. So if you want theta, take your negative 53.1 that you got from the calculator and add 180. So adding 180 to that answer gives me 126.9 degrees. And there's my answer. There's my direction angle. There is a way I could have done this a little easier. I'm in the second quadrant. I do know all three sides of my triangle. One of the inverse trig functions knows about the second quadrant, and that is the inverse cosine button. Inverse cosine knows about angles between 0 and 180 degrees. So instead of writing a tangent statement here, I could have written a cosine statement and said cosine theta is adjacent over hypotenuse. And then when I went to the calculator and did cosine inverse of negative 3/5, I wouldn't need to do any adjusting. It's going to give me the second quadrant angle that I want. Let's verify that. So cosine inverse negative 3/5. And you can see I get the same thing, 126.9 degrees. When you leave the first quadrant, you have to think about the restrictions on those inverse trig functions so that you can make sense of what the calculator is telling you. Finally, part B, using these same two vectors as a starting point, we are being asked to write this new vector called negative 3a plus 2b also in ij form. Well, this is very, very simple. I'm being asked to multiply vector a by negative 3. That's going to be as simple as just distributing that 3 in to both pieces. I'm being asked to distribute that 2 in to both pieces of vector b. Remember, I and j are vectors themselves, so they need the little arrows. This is going to give me negative 15i minus 3j minus 16i plus 6j. And then it's as if I'm adding like terms. I'm just combining the horizontal components for negative 31i, and then negative 3 and 6 makes positive 3j. And that's it. That's the answer. Working with vectors in component form or ij form is actually very, very straightforward. Thanks for watching.